presentation. So today I will talk to you about my recent work on graphical construction of stability certificates in biological interaction networks. So first I will define what's the general problem that we are interested in and offer a motivational example, and then review of previous results. And then I will describe the main results of this work and provide some examples. So the main background of our work is we're trying to study biological interaction networks, also called chemical reaction networks, which appear frequently in systems biology, which is our application that we are mostly interested in. So such networks are suffer from two main problems from the perspective of mathematical analysis. First, they are very nonlinear because of all the nonlinear binding effects. So we have two factors that are bind or unbind, or to a kinase that binds to a substrate, etc. So this gives rise to nonlinearity. And on top of that, we have the problem of uncertainty. So many of the reaction rates and the kinetic parameters are uncertain. So although, for instance, this is an example on the right of a network that you can see the graphical structure of the graph, so what is reacting to what, but the problem is that that you don't know how fast these reactions are happening and what are the parameters that are governing them. So this gives rise of a problem of first of difficulty of analysis. So we have to rely only on graphical information to analyze such networks. And also it is that since these networks are abundant in biology, there have been many arguments that robustness of biological networks is a key defining properties of such networks. So there are reasons to believe that many of these networks that appear in biology are robust in a state, robustly stable in a sense that we're going to define. And this property is important because if you lose stability of a certain, what they call it, a phenotype, this can lead to unsafe levels of the species in the system, or disorder or disease, etc. So this is an example that I want to illustrate, that I would use to illustrate the point here. This is what is called a double phosphorylation cycle. So you have a substrate, and there is a kinase that can attach phosphate groups to this substrate. So this can happen in two ways. The first is known as a processive mechanism. So the kinase binds to substrate, and it just grabs phosphate groups from the environment and keep attaching them to the substrate, and then it leaves, and you get a doubly phosphorylated substrate. And the other mechanism is known as a distributive mechanism. You have the substrate binding to the kinase, and it gives it a phosphate group, and then it leaves and then binds again and gives it another phosphate group. So this is another way, and these two circuits or two networks have different mechanisms, and you can see, and being using the methods that we're going to describe, is that we can verify that this network is globally, it only admits a unique equilibrium in each stoichiometric class, and this equilibrium is globally stable. While the other one, it can admit multiple stable phenotype and multiple stable equilibria. So so what are the tools that we're going to use? Of course, most of you are familiar with the concept of Lyapunov functions. So what we are trying to do is refine a function which is non-negative on the state space. It vanishes at the equilibrium, and the trajectories are decreased, and it is decreasing, or at least non-increasing on the trajectories. And since we don't know the kinetics, we want some structurally robust notion of Lyapunov functions. So that's what we're looking for. So I will describe now what is the class of networks that we're studying. So I mean, for this crowd, you are mostly familiar with this. So this is just a standard reaction, chemical reaction networks. You have a set of reactions, which you think of them as formal linear sums of species going to another formal linear sum of species, and you have a stoichiometry matrix that describe the net gain or loss of molecules between the sides of the reaction. And then we can write the OODE that corresponds to this reaction network. So you have the stoichiometry matrix multiplied by a reaction rate vector. So we assume that we know the stoichiometry matrix, but the thing is that we don't know the reaction rate. So what we assume is that these reaction rates satisfy a minimal set of assumptions. So they are smooth, and if a reactant vanishes, the reaction stops. And the final one is just monotonicity. So the partial derivatives of the reaction with respect to the reactants is non-negative, and this is just recalculates the intuitive requirement that a reaction is monotone with respect to its reactants, and that's the only thing that we assume about the reaction rates. We don't assume mass action kinetics. Okay. So this is an example just to illustrate the points. This is in our work, which is known as a post-translational modification. So so we have a substrate, it binds to an enzyme, and we get a complex, and then you get another phosphorylated enzyme, and we get back our phosphorylated substrate, sorry, and when we get our kinase. And we have another, the backward cycle, which has a phosphate binding to the phosphorylated substrate and dephosphorylated. So we can write this represented graphically, which is known as a pitronate. It is also similar to what is known as the species reaction graph. So here we represent species by circles and reactions by rectangles. I will be using this graphical notation frequently during this talk. So for instance, here the reaction S plus E goes into C1 is represented by a circle of S and a circle of E going into this rectangle and going to C1. So this is an equivalent representation of the list of reactions. And then we have the ODE. So we have the stoichiometry matrix, and then we have the reaction rate vectors, which we don't know. And the set of assumptions that I have given, they can be translated on a sign pattern on the Jacobian. So you have here this Jacobian partial L with respect to X, and we only assume that it is positive on these specific entries and 0 everywhere else. We don't know anything else about this Jacobian. Okay. Okay, so what I want to do is I want to propose what's known as a robust Lyapunov function, which depends here on the rate. So here you can see this is a function which you can think of it as the difference of rates along this main cycle. So this is, for instance, R2 minus R1 minus R2. So this is the reaction rate difference across this species, and then plus the absolute value of the difference across the next species across this main cycle. So the claim that I want to make is that this is actually a Lyapunov function, even if you don't know what are the reactions. So you can show that this function is always decreasing for any given set of monotone reactions. And just to illustrate this, since this is a piecewise function, we can study it region-wise. So let's assume that these reactions have these specific ordering amongst them, and we get that V of X is just R1 minus R4 here. Okay, now we want to study if this function is decreasing or increasing. So, sorry, what happened? So this is the specific region what we're studying, and we can see from this specific ordering of the reactions, we can see that this enforces a specific sign pattern on this species. So, for instance, X1 dot is simply R4 minus R1, and since we assume that R4 is less than R1, we know that X1 dot is negative. So these specific species, the rate of change is either negative or positive, but the point is that we know what is the rate of change. So when we differentiate this function with respect to time, we get that the partial derivative of R with respect to X and times X5 dot. So since we know these sign patterns, so we know that this is negative and this is negative and this is positive. What happens now is that we know that this function is always non-increasing because these partial derivatives are always positive. So what we get is that this function is non-increasing, and we can repeat this kind of analysis over other regions. So this is just another example of a region, and we see that the same analysis checks out. So the point is that the sign of V can be determined without knowing the kinetics. So this is just an example of a function that we're looking for, which is we're calling a robust Lyapunov function. So this is the general definition. So we have a function which is locally Lipschitz. It needs to vanish on the set of steady states, and it is always non-increasing along the trajectories for any given admissible kinetics. So we call this function a robust Lyapunov function. And what I'm trying to do throughout this talk is to provide conditions, graphical conditions for constructing such functions. So I will skip this because of lack of time. So these are two kinds of functions that I will be talking about. Well, the first is called a sum, what I call a sum of currents robust Lyapunov functions. So you can think of xi dots as currents. So it is like you think of it as a charge, and xi as a charge, and then dxi by dt is a current. So This is first type of function, and the second type is what I call a max min function. So you take the maximum of the reaction rates and you subtract from it the minimum, and this can be sometimes a Lyapunov function, robust Lyapunov function. So you might ask why such a function is important and why we are looking for such functions. It allows us to deduce that stability of the network. So first, it rules out multiple equilibria. We can check robust degeneracy of the Jacobian easily, and we can prove that every positive steady state is globally asymptotically stable relative to its stoichiometric class. So this kind of work I have been with my collaborators. We've been developing for a few years. We have developed a computational package that can be used. It uses some computational algorithms like linear programs and others to find such Lyapunov functions. And it has been successful with many networks. These are some of the examples of the networks that we can study. And we can study networks that was not possible to be, they were not possible to be studied using other techniques. And these are some other examples. So, and this is how it compares to other methods. For instance, with respect to the Horn-Jackson finding theory, which is applicable only to misaction kinetics, we can apply it, for instance, to some networks that Horn-Jackson and Feinberg cannot study. Yeah. So this is a quick review of the setup. So the new work that I'm describing is the need for graphical conditions. So for instance, look at this. Let's look at this network. So this is a network which is, we have a substrate and we have here multiple enzymes acting on this substrate to generate products. So we have this one substrate and many products. Products can be product 1, 2, 3 till n. And if we want to use these computational algorithms that I talked about, it is first, you cannot use it for an arbitrary n. You need to specify the network precisely for such methods to work. And the second is that you don't know why this method is working, even if you can figure it out. So what we're trying to do here is to provide a set of graphical conditions so that you can understand the conditions graphically and you can interpret them without having to go through computations. And also, if you add simple modifications, like if we add some inflow and outflow reaction on this network, for instance, to the substrate, will it violate the stability conditions or not? So that's the question that want to study. So the first function I want to talk about is the max minus min Lyapunov function. So for simplicity, first let's talk about a network whose dimension of the kernel of the stoichiometry matrix is unidimensional. So we have only one vector in the kernel of the stoichiometry matrix. So we can propose this function, which is the max of the reactions minus the min of the reactions. So for such a network, the graphical condition is that for each species, there exists a unique output reaction. So for instance, the 1A, the subfigure A, this is a permissible situation. You have several reactions feeding into this species and this species going to another reaction. So for each species, there is only one outward arrow going out from it. So if you think of the stoichiometry matrix, this means that each row has only one negative number in that row. While, for instance, this second situation is now permissible, where you have a species that has two arrows coming out of it. So you have two negative number on the row of the stoichiometry matrix. So that's the first called max minus min reaction. The second one is which is actually well known in the literature, which is the set of called monomolecular networks or compartmental networks. So these are networks that have only reaction of this form. Also, they call them interconversion networks. Xi goes to Xj, or creation or decay. So these are the only reactions allowed, and it has been shown that this Lyapunov function, which is the L1 norm of the time derivative of the state, is non-increasing along the dynamics, and we can see that this fits into our framework, which is this is a piecewise linear function in terms of the rates. So now, given these two classes of networks, the max minus min and the monomolecular networks, I want to describe some set of graph modifications that we can use, and if we apply them to a given network, we can preserve the stability of the network and preserve, or we can find a Lyapunov function. So these are the set of modifications. So first is reversal of a reaction. The second is adding an intermediate. The third is external regulation of a species, etc. The last two are, for instance, you have adding a catalyst. So here we have a species that is, and we add another species that is that catalyzes the expression of this species. So, for instance, you can think of this as a complex, and this is as a kinase, for instance, here. And you can notice that if this modification, the last two, they make a monomolecular network into non-monomolecular. So if you have mass action kinetics, it makes a linear network, a linear dynamics into non-linear ones. So for instance, here you can think of adding a dimer. So when you add a dimer, you convert a monomolecular reaction into a bimolecular reaction. So okay, so these are the formal definition of these modifications. I will not go through these, so that this is they are defined rigorously here. And furthermore, we can define, we call a network and tell a modification of another network if you have a finite sequence of elementary modifications. So each modification that appeared in the previous table, we call it an elementary modification. And if you have a sequence of these, you have an elementary, you call the new network as a modification of the previous network. So for instance, you can combine 3 of these elementary modifications to get what is known as the standard enzymatic catalysis reaction. So for instance, you can think of the abstract reaction as a species, substrate going into a product. Okay, so these are two reactions. This is the reaction, and we can think of it as adding intermediate. So we have an intermediate, which is the complex. So C goes to S, goes into C, goes into P, and then we add reversal to the first reaction. So and then we add a catalyst. So the catalyst is here the enzyme. So this is, you can think of first reaction S goes into P, and its modified version is S plus E, got back and forth to C, and then to product plus enzyme. So this is a modification of the previous one. Okay. So this is the two main results that the main results on regarding linear networks. So networks which are monomolecular or compartmental. So you can apply many of these modifications without impacting the stability of the network. And in particular, these two modifications, adding a catalyst and adding a dimer, which convert actually a linear network into a nonlinear network, we can find, we have actually a robust Lyapunov function for such modified networks. And I will show examples of this so that you can see this gives rise to fairly sophisticated and complicated networks. So this is a corollary of the previous results, so that in any linear networks where you have a reaction of the form xi goes into xj, you can convert it into an enzymatic catalysis reaction, and you would still have a Lyapunov function for the new network. So this is a kind of modifications that our theorem allows, and it is also very relevant to systems biology. Okay, so the next class of Lyapunov function is known as the max minus min, and also we can perform many of these modifications, including adding a catalyst, dimer, intermediates, etc. And also we can reverse some of the reactions, and with the Lyapunov function will be modified in this specific manner. And for the second kind of Lyapunov function, we can actually allow for even more elaborate kind of enzymatic catalysis. So if you have this kind of a reaction, which is just an input complex goes into an output complex, you can add an arbitrary number of intermediate complexes between them, and they are catalyzed by the same enzyme. So this is known as a processive enzymatic reaction. So if you have if your initial network has a Lyapunov function of the form of max minus min, then you can replace any reaction by a reaction of this form, and you will still have your Lyapunov function. So, using this analysis, we can, in fact, many of the properties generalize. So it is not just the Lyapunov function. We can show that robust degeneracy of the Jacobian carries over, even for if you just only assume robustly P0 Jacobians, you don't need even the Lyapunov function for many of these properties. And we have persistence. So there is this property of structural persistence, which is lack of critical siphons, then this also carries over. So all these nice properties carry over from this smaller network to the larger network. So I will not go through the details of these properties. Because of lack of time, I will just want to focus on the examples because they are most interesting. So this is the network I started with. You can see that it is fairly complicated, but you can notice that there is a pattern. So this reaction from substrate to the product takes the form of an enzymatic catalytic reaction. So what we can think of this network, which is a fairly simple network, is just a substrate going back and forth to various products. It is a linear network. You can study it using various techniques. It is also deficiency zero. It is compartmental, etc. But using this kind of a transformation from xi goes into xj, we replace each reaction by this kind of enzymatic reaction, and we get this big network. But using our theorem, we can say that since the initial network has robust stability, we have a Lyapunov function. So for the new network, we have this statement that each stoichiometric class has a unique, globally stable positive equilibrium. And this carries over for any kinetics and for any order of the network, for any n. So this is a kind of result that we get from using our theorems. This is another simple cycle. Think of this as a linear cycle. So we have S0 goes to S1 and back into S0. And if we use this kind of a processive modification in the processive cycle modification. So you replace such a reaction, you can see in this small box with these reactions, we get, this is called in the literature an all-encompassing processive cycle. So you get this kind of, you can get stability and all these nice properties carry over from this simple network to this fairly complicated network. And we don't need to do any computations to verify that just by looking. This is another example. This is a simple network. S0 goes into S1 and etc. to Sn. This is what we call a linear chain of reactions. If we replace each reaction by an enzymatic catalysis reaction, we get this chain of PTM cascade of post-translational modifications, and we get the same nice properties carry over to the new network. This is another network. This is a paper that this is known. The one on the right is known as the T-cell kinetic proofreading network. It is Eduardo Sontek has published a well-known paper in 2001 analyzing this network using zero deficiency methods, complex balance methods. But using our methods, we can see that this the MHSC molecule and the ligand are using our notation. They are just dimers of each other. So what we can think of this as a linear network, and we replace this specific species by we replace it by two species that we can think of them as heterodimer in this context, and we get all these nice properties of stability for any kind of kinetics. It's not just mass action kinetics. So this is just carries over as a corollary of our results. This is another model is known as the Ribosome Flow Model. There have been several papers dedicated to studying this using monotone system techniques. So we can think of this as a chain of reaction. So this is a unidirectional chain of reaction. So you have an inflow, and then it goes into various form, and then goes to an outflow. And if we apply the adding a catalyst for these reactions, we get this kind of reaction network admits a Lyapunov function, and it is always it has always unique stable equilibria in each stoichiometric class. And this actually generalizes for fairly complicated forms of the ribosome flow model. For instance, you can think of this as the initial form, which is a ribosome pool back and forth to an mRNA. So you have to think of a ribosome pool. It is feeding. It is working on a set of different mRNA strands, and then by using the modifications we have, we can add a set of interconnected ribosome flow models. So if you look at the last small figure here, you have each mRNA. It has its own reaction network of an arbitrary number of reactions, and we can have an arbitrary number of these mRNA strands, and all of them are feeding on this ribosome pool, and all of them, and for any number of these strands or number of this reaction, we get stability and we get a Lyapunov function for all of them. So I think I have, it's 25 minutes, and so thank you for listening.